Today we're going to be talking about simplifying radicals that do have variables involved. And it's going to feel very, very similar to what we just did without variables, but you're going to still want to sort of note the rules in more general form on what's going on with those variables. So what will it look like still when it's perfectly simplified? You still want no perfect powers underneath that root, so any perfect squares in front of the square root, perfect cubes in front of the cube root, perfect fourths in front of the fourth root, etc., etc., etc. You shouldn't have any fractions in the radicand, and there should be no radicals in the denominator. We're still going to exploit the radical product property, where we're able to break up that multiplication under the radical into two different radicals. It's very equivalent to sort of say that about fractions as well. So we're going to be exploiting both of those rules, and then we're going to be really exploiting the fact that we're wanting to break out perfect powers in front of that root. So in particular, even if we're looking at something more abstractly, what we're looking for is the exponent on our variable to match the exponent on the root. So if, for example, I have the 7th root of x to the 7th, I'm going to break that up as an x in front of that root itself. And then you would end up with just nothing actually in that case still underneath the root. And then thinking about my exponent rules, if I were to have something like x to the third power for a square root, what I would want to do is break that into the square root of x squared times the square root of x, since x squared times x gives me x cubed, and then the square root of x squared I would note would just become x. Square root of x would stay underneath there as is. Now technically what I just assumed there was I assumed x is greater than 0, and a lot of times in these problems that's actually what we're assuming. Otherwise I would technically have to break out an absolute value of x instead. But typically that's sort of a technicality a little bit beyond what you would normally encounter in a intermediate algebra course. Really what you're going to usually assume is that your variables are positive. And I'm going to go ahead and actually for these ones I'm going to actually go ahead and write that as well. So assume all variables are positive. Otherwise, you do have to get into technicalities about when to write it as a absolute value sign or not. The short of it is being that if the index on the root is even, and if you broke out in front of the root something that is not itself squared, you would technically have to put in absolute value signs. But again, that's not really the focus today. What we're instead going to focus on is finding all of our perfect squares to break out in front of the root, and then everything else will stay as is under the root. So let's take a look at this first example. So we're first going to break that into the square root of 9 times the square root of m squared. Square root of 9, we're aware that 3 times 3 gives us 9, so that would be 3. Square root of m squared, assuming that m is positive, would just simplify to m, since squaring a square root undoes each other. If we weren't assuming m is positive, we would just have to make sure to put m in absolute value signs. But otherwise that would just become 3 times m. And that's really the last time I'm going to make note of that, just because in all of your problems that you'll be practicing for this, it does say assume that variables are positive, so we're going to roll with that assumption. For this next one, we're similarly going to break this down into the square root of 192 times the square root of x to the fourth. For the square root of 192, I'm going to go ahead and prime factorize 192 a bit to the side here. So 192 divided by 2 is going to leave us with 96. 96 divided by 2 is going to leave us with 48. 48, I'm aware, breaks down to 6 times 8. 6 breaks down to 3 times 2, and 8 breaks down into 4 times 2, and 4 breaks down to 2 times 2. And then I'm going to go ahead and just cross off anywhere I had a middle step so that I don't confuse that with the final factorization. So it looks like 192 will break down into 2 to the 1, 2, 3, 4, 5, sixth power times 3. And then I'm even going to double check myself to the side that if I indeed do 2 to the 6th times 3, I get 192, so I'm good. So I'm going to rewrite this then as the square root of 2 to the 6th times the square root of 3 times x to the 4th. For 2 to the 6th, if I take the square root of that, that's asking ourselves what number times itself gives me 2 to the 6th. And that would be 2 to the 3rd. Now, how did I kind of know that in my head? Well, I know, let me actually write that to the side here. I know in the way that exponent powers work that I'm looking for 2 times itself to some power. And in terms of multiplying the same base, what we're going to do with those exponents is add them. So really I just need to do 6 divided by 2 to give me 3. To note that this really means that 2 to the 3rd times 2 to the 3rd gives me 2 to the 6th. Square root of 3 is going to stay as is, and then similarly with the x to the 4th, I want to do the same thing of x times what power times x times itself will give me 4. Well, x squared times x squared, 2 plus 2 is 4. So really all I had to do in my head as well was 4 divided by 2 is 2. So that will become x squared. Then if I'm going to kind of simplify this in its final form, 2 to the 3rd is 8. I would write the x squared first, and then by convention write the root last. So in short, in order to kind of figure out what's going to break out front, you really just need to take whatever this exponent is and divide it by the index on the root. In this case, this root is even, so I can divide it by 2, no problem. Let's go ahead and go a little bit further with this. So I'm going to encourage you to go ahead and pause your video and try these next 3. And you might notice in particular with the first one that some y's will break out front and some are going to stay underneath the root. So for this first one, I'm going to break this down into the square root of 64 times the square root of y cubed. For the square root of 64, I know that 8 times 8 is going to give me 64, so I'm going to rewrite that as the square root of 8 squared. For y cubed, well, if I do 3 divided by 2, I'll find that that gives me 1.5. So in particular, I'm going to be thinking to myself, okay, well, I'm going to have one part that's going to break out in front of the root, and one part that's not. So I'm actually going to rewrite this as 2 different y's. One that actually is a multiple of the index on the root, in this case 2. And one that's what's left, because what I really just did was I rewrote y cubed as the same thing as y squared times y. Now I'm ready to do my final simplification, because the square root of 8 squared is just going to leave me with 8. The square root of y squared is going to leave me with y. And the square root of y stays as is. And again, for all of these practice problems, we are assuming all variables are positive, greater than 0. Let's go ahead and try this next one. So for this one, 16 I know breaks down to 4 times 4, so I'm rewriting this as the square root of 4 squared times the square root of a squared times the square root of b to the 4th. The square root of 4 squared will give me 4. The square root of a squared will give me a. The square root of b to the 4th gives me b squared, since b squared times b squared gives me b to the 4th as my final beautiful answer. Now when I have a 4th power, I'm instead wanting to think about what times itself 4 times gives us this number. So in particular, with 8, I know it breaks down to 9 times 9. And 9 times 9 breaks down to 3 times 3, so I've got myself a group of 4 3's giving me 81. So I can rewrite that first term as the 4th root of 3 to the 4th. Similarly, for the m squared, he's going to break down into m times itself 4 times, so I can write that as the 4th root of m to the 4th. For the n to the 8th, that's really going to be that I can break down n to the 8th into n to the 4th times n to the 4th, and that n to the 4th breaks down into n squared times n squared. So in a similar way that I broke down the 3's, it's really 4 n squareds times itself that gives me n to the 8th. So I'm really going to be thinking about that in terms of n squared to the 4th power. Now whenever I do my final simplification, the 4th root of 3 to the 4th is just 3. The 4th root of m to the 4th is just m. And then the 4th root of n squared to the 4th will give me n squared. Alternatively, what you could have done is that 8 divided by 4 gives you 2, which if you notice is exactly the same thing as what ultimately ended up breaking out front of that root. So my final answer would be 3mn squared. Whenever it comes to fractions, don't forget I can still rationalize, and I can still rationalize even if there are still things underneath the root that are variables as well. So let's go ahead and practice that a little bit. So for this first one, and actually this first example is actually what I'm going to focus on because that has not been filled in yet. In terms of the just plain simplification here, I would actually simplify that first, because if I have an x to the 3rd power over x, I already know that that's going to simplify to x squared in my numerator, since 3x's divided by 1x just leaves me with x squared. Similarly, if I want to distribute that root a little bit more around, square root of 100 times the square root of x squared all over the square root of 11. Square root of 100 is 10. The square root of x squared leaves me with x, because it's saying what number times itself gives me x squared. That would be x all over the square root of 11. Now we're ready to rationalize by multiplying both the numerator and the denominator by the square root of 11. And you would be left with 10x square root of 11 over the square root of 11 squared leaves you with 11. So similarly on these next ones, we're going to want to simplify kind of as much as we can before we bother with the rationalization, because that may or may not actually be a step we have to do. So we'll rewrite this by distributing the root to everybody. So we have the square root of 4 times the square root of a to the 4th times the square root of 9 times the square root of b squared. And again, for all of these, we are assuming the variables are bigger than 0, as a point of technicality. The square root of 4 is just going to be 2. The square root of a to the 4th, remember a to the 4th would break down to a squared times a squared, so that would give us just a squared there, over the square root of 9 is 3. Similarly, the square root of b squared would just be b, and that would actually be perfectly simplified as is, no rationalization necessary. For the next one, we again might find the same thing happening once I actually simplify underneath the root a little bit more. So 32 divided by 2, that's going to give us 16. X cubed divided by x will give me x squared, and then I can break that into the square root of a 16 times the square root of x squared. Square root of 16 is 4. Square root of x squared is x. So on a lot of these, that wasn't actually necessary. Let's go ahead and write one more, though, where maybe it is necessary. So let's say I had 92 x to the 5th over 2, actually let's make that 3y, all underneath the square root. So 92 over 3, that actually doesn't simplify. We might want to see if 92 simplifies at all. So 92 breaks down into 2 times 46. 46 breaks down into 2 times 23. So I can rewrite that as the square root of 2 squared times the square root of 23. 2 squared times the square root of 23, and I might even want to double check to the side here that 23 times 4 does indeed give me 92. As for the square root of x to the 5th, I want to break that into the square root of x to the 4th times the square root of x. Why is that? Well, if I try doing 5 divided by 2, I'm going to get 2.5. So that tells me that there should eventually be two x's that are going to perfectly break out front, and then there's going to be one that actually stays underneath. That whole number sort of telling us how many of this will ultimately simplify out to being no longer underneath the root, and the fact there's a remainder saying there's still some underneath. So I essentially want to break it into my highest multiple of the index, which in this case the highest multiple of the index that goes into x to the fifth is x to the fourth. So the highest even number really that goes in when it comes to squares. I'm just trying to phrase it a little bit more generically for when we get into cubes and that sort of thing. And then we still have an x left, because ultimately x to the fifth is the same thing as x to the fourth times x. All over, and then we've got the square root of 3y, and I'm actually going to even just leave that as is because that doesn't really simplify. Then if we continue to simplify this, the square root of 2 squared will just give me 2. The square root of x to the fourth is going to give me x squared, because x squared times x squared gives me x to the fourth. And then I still have 23x underneath that root. All over, and then we still have the square root of 3y underneath that root. And I'm actually just going to erase this factor tree to give me a little bit more room, but then I'll rewrite that we know that 92 is the same thing as 2 squared times 23. Now we're ready to rationalize. So in particular, I'm going to multiply both the top and the bottom by that root that we have. So if we now have on the bottom the square root of 3y all squared. On the top, I can go ahead and multiply the 3 times 23 underneath that root to give us 69. So we're going to wind up with 2x squared, square root of 69xy. 69, I don't believe that actually really simplifies further. Yeah, because, well, it breaks down to 23 times 3, and 23 and 3 are both prime. So that's actually as simplified as it gets. But then we do want to note if I have the square root of 3y all squared, that's just going to end up simplifying. Actually rewrite that top there, nice and neat. 2x squared, 69xy, all underneath the root, and then we've got 3y there remaining on the bottom, because basically when we multiply by that same root, that cancels out and you're just left with 3y there, because if you take the square root of 3y all squared, that's saying what times itself gives me 3y all squared, 3y. So that would be our final beautiful answer. So in short for these, you do want to simplify as much as you can first, and then see, is it even necessary to rationalize? If it is necessary to rationalize, still again simplify as much as you can before you do that rationalization process, just in case there is something that cancels out. And if not, you just multiply both the numerator and denominator by whatever that denominator is, which will make the root part cancel out so that you have no more roots left in that denominator. If you have higher ordered powers, you want to be thinking about how many times does this go into that power. So in this case, if it's a cube root, you want to figure out what times itself 3 times gives us that. And it's still going to help to sort of think in terms of, well, if I take this initial exponent and divide it by that many groups, how many of those groups are going to evenly come out? So in particular, for this first one, for 64, well, I know that 64 is going to break down into 16 times 4, and that 16 breaks down to 4 times 4. So I know 4 times itself 3 times is going to give me 64. So that's going to be helpful. For the x to the 12th, I'm going to notice that doing x to the 4th times itself 3 times gives me x to the 12th. How else could I have done that? Well, 12 divided by 3, that index is 4, so that's going to tell me x to the 4th will be my candidate there. So we're going to do the cube root of 4 cubed times the cube root of x to the 4th cubed. So again, that 4th came from doing 12 divided by 3. For a final answer of the cube root of 4 cubed, it would just be 4. The cube root of x to the 4th cubed would be x to the 4th. So some people sort of skip this middle step and they just sort of notice, Well, whatever group of 3 that I had there, that's going to be the thing that ends up breaking out in front of that cube. So let's try some more of these. So if I had the cube root of 125, well, I should note that 5 times itself 3 times will give me 125. So I'm going to rewrite that as the cube root of 5 cubed. A to the third is already nice and neatly done, where if I take the cube root of a to the third, that should just give me a. For b to the sixth, I should note that b squared times itself 3 times will give me b to the sixth. Another way I could do that is 6 divided by 3 gives me 2. So I'm going to have the cube root of, in this case, b squared to the third. So cube root of 5 to the third is just 5, cube root of a to the third is just a, cube root of b squared to the third is b squared. So in short, whatever I did find multiplied by itself 3 times to give me that is what ended up breaking out in front of that root. Now this next one is a good example where not everybody is going to break out in front of the root. So for the 8, well, 2 times 2 times 2 does indeed give me 8. So the 2 is going to go in front of the root. For x to the 9th, well, x to the third times x to the third times x to the third will give me x to the 9th, because you end up adding up all the exponents, right? So if you want to think about it more formally, what you have is the cube root of x cubed cubed. But at the end of the day, what does that mean you're left with? Is an x cubed. For the y to the fourth, if you do 4 divided by 3, that's not going to go in evenly. So we really want to break down that y to the fourth is the same thing as y cubed times y. So we're going to have a cube root of y cubed, and we're going to have a cube root of just y, while the cube root of y cubed is going to just become y, and then the cube root of y will stay underneath. The way you'll know that you did this right is if underneath the root, every power underneath that root is strictly less than that root. If not, that means that you have more to break out. So if, for example, you wrote this as 2x cubed times the cube root of y to the fourth, 4 is greater than 3. So your power underneath the root was greater than the root itself. That would mean that you need to simplify more. Once you start getting into the much higher ordered powers, I think it is helpful to also sort of visualize it by a factor tree. So in particular, for this 64, I might notice that that breaks down into 8 times 8. 8 times 8 break down to 4 times 2, 4 times 2. 4 breaks down to 2 times 2, 2 times 2. And then I'll notice that I can break that down into one group of 2 to the fourth. So I've got one group of 2 to the fourth to the fourth. So I've got the fourth root of 2 to the fourth, if you will. And then I have remaining 2 lonely 2's that won't end up simplifying. So I've broken down the fourth root into 64 into 2 groups. One that will be everything that's going to end up eventually just canceling out to leave us with just a 2, because the fourth root of 2 to the fourth is just 2. And then the other one will have to simplify just a little bit under the root, but will stay under there. And that'll be the fourth root of 4, and the fourth root of 4 is not a nice even number. There is no integer that I know of that times itself 4 times gives us 4. Similarly, for the m's, m to the 6 breaks down into m to the fourth times m squared. And remember, m to the fourth is really 4 m's versus m squared would just be 2. So wherever you see that I've got myself a group of 4, you should be predicting that's going to be a part that simplifies nicely. So I'm going to have the fourth root of m to the fourth from that first part, and then I'll have the fourth root of m squared from that second part of the unmatched m's. Fourth root of m to the fourth will just give us m. Again, we're assuming all of these are positive integers. While the fourth root of m squared is not going to simplify at all. And if you notice, that's actually identical math there. The first one really is 2 to the 6th power. How did we break up 2 to the 6th power? Well, 4 of those 2's are going to perfectly break out front of the root because the root is to the 4th index. So that 2 to the 4th root of 2 to the 4th just becomes 2. Well, the other 2 remaining 2's don't go into 4 evenly. They're a remainder. So they're going to stay as is underneath the root. Similarly with the m's, 4 of those m's are going to be such that m to the 4th root of m to the 4th just becomes m. So they break out front as one big old group, while 2 of those are going to stay underneath the root. An alternative math that you could have done that's a little bit more systematic is you could have taken the 6th power divided by the 4th index, so index power, and that would have given you 1 remainder 2. That 1 tells you what goes in front of the root, and the 2 tells you what's still in the root. For the last one, if I have n to the 9th, well, I can break that down into n to the 8th times, or actually let me just be a little bit more explicit. That's going to be 2n to the 4ths times the remaining n. So that's exactly how I'm going to rewrite that, is I'm going to have the 4th root of n to the 4th, the 4th root of n to the 4th, times 1 more n, and we know that the 4th root of n to the 4th just becomes n, and then we still have 1 more n to the 4th, or we just have 1 more n underneath the 4th root, I should say. Now I'm just going to rearrange it where I put everybody who's in front of the root together, so I have 2mn squared, because we have n times itself 2 times, times the 4th root of 4m squared n as our final answer. Another way you could have gotten to that conclusion with the n's is that 9 divided by 4 does give you 2 remainder 1. So that 2 remainder 1 would be exactly there on the n's. So the remainder goes underneath the root, and that answer ends up going in front of the root, how many times it goes in evenly. So I'm going to encourage you to pause your video and try these next 2 yourself before we go over it. My hint for the first one is it may help to actually re-put these all underneath the same root, simplify a little bit, and then deal with the root itself. So this first one, if I'm going to follow my word of advice, I'm going to rewrite that as 10z to the 7th, a to the 10th, over 5z to the 5th, a to the 6th. If I start simplifying underneath, 10 divided by 5 is 2. Z to the 7th divided by z to the 5th is z to the 2nd. A to the 10th divided by a to the 6th is a to the 4th, because if I have 10 a's divided by 6 a's, 6 of them cancel, you're left with 4. And I actually have no more fractions anymore, which is nice. Now I'm just going to separately simplify all of these. Square root of 2, square root of z squared, and the square root of a to the 4th. Well, the square root of 2 actually does not simplify. And by convention, we actually write the root last, so I'm going to write that kind of at the end. Square root of z squared, well, z times itself 2 times is what gives us z squared, so that'll break out front. Square root of a to the 4th, 4 divided by 2 is exactly equal to 2. And a squared times a squared does give me a to the 4th, so the square root of a to the 4th is simply a squared. For this next one, we want to ask ourselves what times itself 4 times gives us 81. Well, 81 is 9 times 9, and 9 times 9 breaks down into 3 times 3. So we know that the 4th root of 81 is actually just 3. For the 4th root of 12, x to the 12th, well, x to the 12th breaks down into x to the 3rd time, or x to the, x to the 3rd times x to the 3rd times x to the 3rd. And 12 divided by 4 gives you 3, so that could be another way of thinking about it. So this is really the 4th root of x to the 3rd to the 4th, so that will end up being an x to the 3rd that perfectly breaks out front. For the y to the 15th, well, 15 divided by 4 does not give you an even number, so we really want to figure out how many y to the fourths are going to break out front there. So in particular, we have y to the 15th is the same thing as y to the 4th times y to the 4th times y to the 4th, with a remaining y to the 3rd that still has not been broken out front. So I can go ahead and rewrite this as the 4th root of y to the 4th times another 4th root of y to the 4th times another 4th root of y to the 4th times a 4th root of y cubed to give us a total of 15th, and we know that the 4th root of y to the 4th is just y, and then we'd still have a 4th root of y cubed left. So if I'm going to write that more succinctly, y times itself 3 times will give us y to the 3rd, aka I had 3 of those, so that became y to the 3rd, 3x to the 3rd, 4th root of y to the 3rd, all left underneath there. For this next one, similarly, I would still recommend sort of re-breaking stuff underneath the root and seeing if that helps your simplification. So that would become 1/2, because there's a 2 out in front of the root, times 108a cubed over 2a. Then if I start to simplify underneath that root, which again I'm only able to do because the index on the root is the same, that would become 1/2 times the square root of 54, and then a cubed divided by a leaves us with a squared. Might want to see how 54 will end up simplifying. So 54 I know is 9 times 6. 6 breaks down to 3 times 2. 9 breaks down to 3 times 3. So that 3 times 3 tells me a part that's going to simplify, because that is a pair of 3's for a square root. So I'm looking for groups of 2, while the 3 times 2 will not simplify. So I will have 1/2 times the square root of 3 squared times the square root of 6, the 3 squared being the part that I know is going to simplify, the 3 times 2 being the part that I know is not, times the square root of a squared. The square root of 3 squared leaves us with 3. 3 times 1/2 gives us 3/2. And then we still have the square root of 6, and actually let me deal with the stuff that's going to simplify a little bit first. A squared, the square root of a squared gives us a, and then we still have the square root of it 6 as is, and now I have no more roots in my denominator as well. So just to recap, what you want to do is for whatever is the power of root, for whatever nth root, you want to take whatever number is in there and find some number or variable times itself n times to give you that number or variable. You have a couple different ways of doing that. For variables, oftentimes it's helpful maybe not to literally completely prime factorize it, but to go ahead and see what you can break them down into. So in particular, like for x to the 12th, I was looking for, again, groups of 4 something. So I actually was able to kind of come up with, okay, well, x to the 3rd times itself 4 times, that's a group of 4, will give me that x to the 12th. Alternatively, a different way to think about that would be to think about, well, how many y to the 4ths or whatever to the 4ths fit in there evenly, and then what's left over. Both of these are equally valid, just whichever way your brain tends to jump to would be what I would do. The second way is a little bit more systematic if you want to kind of do it that way consistently, or the first way is fine too. The first way kind of comes from directly doing that exponent divided by the index on the root. The second way kind of just comes from conceptually breaking down whatever that initial exponent is. As for the numbers, you want to still approach that the way that we've been approaching that, and that factor trees can be a really helpful way to find whatever group, however many, some number that times itself the number of index times, which of those is going to be able to break out front, versus which numbers are going to have to stay underneath. Those are going to be whatever your unpaired numbers. So for example, in example 3, when I was looking for groups of 2 because it was a square root, we had a 3 times 3, great, that will end up being able to be broken out front, but that remaining 3 times 2 that wasn't paired with anything is going to go underneath. And if your factor trees get long, it can be helpful to sort of cancel out those middle steps of the factor tree so that you don't end up confusing it with the ultimate factors that are in there. And then for all of these, just make note we were assuming all variables were greater than 0 for especially those even roots, because technically otherwise you would have to use an absolute value sign for that. But that's a technicality that won't appear in the practice problems that you'll be doing, but you may eventually come across it in another class.